Let's look at a review on how to name binary compounds. We'll just start from the top. We're going to start, let me zoom in here just a little bit, make it a little bit easier to see. So this is a flow chart like it's in your book, and I've added a few things to it just to help us remember as we go through. So remember, the first thing that we always ask ourselves is it binary? So is it a binary compound? Remember, binary means only two different elements, and that's it. So two different elements. So yes, it's binary. Then we ask ourselves, is there a metal present? If the answer is no, it's an easy one. It's a type 3. And we use the prefixes like mono, di, tri, tetra, penta, hexa, hepta, octa, nona, and deca. That's the type 3 prefixes. Remember, these are the easy ones to do. We changed the second one to "ide," but these are on the right-hand side, so there's a sharing of electrons instead of a transfer of electrons, so we don't worry about charges. And we use a prefix all the time except for mono on the first element in the compound. We don't use mono. If there's just one, we leave it that way. For example, if we have CO, I look at it and I say, is it binary? And the answer is yes. Is there a metal present? No. It's carbon and oxygen, and those are both on the right-hand side of the periodic table. So we're going to use prefixes. There's one carbon and there's one oxygen. But we never, if this first one is, there's only one of this one, we never use mono. If it were anything else, we would. So we just name it carbon. Now there's only one of the second one, and we always use a prefix even if it's just one. So it's monoxide. We change the ending to "ide." Alright, so let's go back up here. Is it binary? Yes. Is there a metal present? Let's say that there is a metal present. What I have to do is I have to ask myself, am I dealing with a true metal or a transition metal? So when it says, does this metal form more than one cation, that is, does it have more than one possible oxidation state? So is it a transition metal is what they're asking. If it doesn't form more than one ion, it's considered a true metal, and that's in groups 1 and 2 and aluminum. So those we always know the charge on, so those are the type 1s. Now if it's a metal that has more than one cation, it's considered a transition metal, and those are the ones in the trough. So we have to determine the charge on that one, and this is where our Roman numerals come into play. When we name a type 1, let's go back and review this. We'll pick a standard such as NaCl, and let's just go through the flow chart. We ask, is it binary? Yes. Is there a metal present? Well, here's Na, which is sodium, so the answer is yes. Does the metal form more than one cation? Is it a transition metal? No, it's a true metal. So we use the element name for the cation. So all I have to do is say sodium, chlorine becomes chloride, and that's how we would name that. Okay, let's look over here at the other side. So what if we have a transition metal? We're going to name it as a type 2, and this is where we determine the charge of the cation. Remember that these transition metals, we don't know their charge, so we have to rely on the nonmetal or the polyatomic ion, like we'll talk about in a little bit, to determine the charge on the transition metal. So determine the charge of the cation, use a Roman numeral after the element named for the cation, and it's for that charge. So the Roman numeral is for the charge on the transition metal. So for example, if we have iron 3 chloride, we look at it, and the first thing you have to say is it binary? Well, it's chloride. So what did chloride used to be? Chlorine. And iron, we know. And we notice that iron, as we go down through here, iron is a transition metal. So what we have to do to put this back together, going backward from how we started here, is we have to look at the charges and say, okay, what would my formula be? Well, I always rely on my nonmetal because my nonmetal's charge never changes. So chlorine used to be chloride, used to be chlorine. It has a -1 charge. Iron in this case has a +3 charge. So when we get to this point, we're actually given the information. So then we have to do the math problem and say, okay, what is the smallest number that 3 and 1 will go into? And the answer, of course, is 3. So what do I have to do to the right-hand side to get it to become -3? well, I would have to have 3 chlorine. And what would I have to do to the left-hand side to have a positive 3? I would need 1 iron, so it would be FeCl3. Now going backwards, let's say that we have, for example, ZnCl2. Now, even though zinc, if they don't give you a charge, we always say that it's positive 2, we're going to go ahead and treat it as a transition metal when we name it. So we look at this and we say, is it binary? And the answer is yes. Is there a metal present? Yes. Does the metal form more than one cation? It can. So we say yes, it's a transition metal. So we're going to use the Roman numerals to determine the charge. So we're going to write down zinc. We're going to leave room for the Roman numeral. Chlorine is chloride. And now we go back and we do the math. Chlorine is our nonmetal that always has the same charge. We know that chlorine has a -1 charge, and we know that there are 2 of them. That makes this side a -2 charge. On the left-hand side, we know that we have to make it a +2 charge. So a +2 and a -2 cancel out. So we say, okay, well, we have 1 zinc. What must its charge be to make this side a +2? And that would be a 2. So it's zinc 2 chloride. Now, naming binary compounds and naming compounds with polyatomic ions doesn't really change much. So we covered that a little bit later after we covered just the binaries. So remember, your polyatomic ions are going to follow the same thing. Now, type 3s are not going to come up as polyatomics because type 3s are going to be only with 2 nonmetals. When we ask if there's a metal present and the answer is yes, then we need to determine what type of metal that is. And those are usually hooked to, in this case, if it's not a binary compound, they're going to be hooked to a polyatomic ion. There are polyatomic ions, remember, that have a positive charge. We treat those as a true metal when we name them. So we name them just like this, when we, as if we would start it with sodium or something like that. Ammonium is the ion that usually is that way. So let's look at a couple of examples of polyatomic ions. Let's say that we had, for example, let's try Al2SO43. So we would look at it and we would have to recognize that it's not binary. If it's not binary, then we start looking for polyatomic ions. So let's determine first of all that it's not binary because we have 3 different elements, aluminum, sulfur, and oxygen. And when we look at this, we also notice that aluminum is considered one of our true metals. So we're going to just name it like we would a type 1. So we're going to say aluminum, and SO4 is sulfate. And that's all we have to do to name that polyatomic ion. If we have one, let's say FeOH3. Let's look at this example. So we have FeOH3, and we look at it and recognize right off that it's not a binary. It has 3 different elements in it. So then we have to determine if there's a metal, and there is, and it's iron, and that iron is in the trough, or it's a transition metal. We know it can have more than 1 charge. So we rely on this portion of the compound to tell us what the charge on iron is in this case. So go to our polyatomic ion chart and we find OH. And OH is hydroxide. So let's go ahead and write that down. Iron, charge, hydroxide. So hydroxide has a -1 charge, and there's 3 of them. So this side is a -3 charge. So the question is, what does iron side have to be? And it has to be a +3. I have 1 iron in this case, so its charge must be a +3 in order to make that balance out to 0. So this is iron 3. I don't know if you can see that. There you go. This would become iron 3 hydroxide.